Imagine for a moment the grandest tapestry ever woven. Threads of galaxies, clusters of stars, all interconnected, stretching further than human comprehension can truly grasp. Now picture this tapestry not as static, but as constantly, relentlessly unfurling, growing larger with every passing second. This is our universe. Its expansion is one of the most fundamental yet profoundly perplexing discoveries in all of science. It forces us to confront a question so basic, yet so mind-bending. It can keep you staring into the night sky for hours if the universe is expanding. What exactly is it expanding into? Is there an edge, a boundary beyond which lies something else? Or is the very question flawed, a limitation of our three-dimensional thinking? This isn't just an academic puzzle, it touches upon the very nature of reality, our place within it, and the ultimate destiny of everything we know. The shocking truth, or perhaps the more unsettling lack of one, awaits our growing understanding of this cosmic ballet. The journey to this profound realization began not with a sudden epiphany, but with careful observation and the slow accumulation of evidence that would eventually shatter existing paradigms of a static cosmos. In the early 20th century, the prevailing scientific view, even embraced by Albert Einstein initially in his theory of general relativity, was that the universe was largely unchanging on the grandest scales. It was a comfortable, if somewhat unimaginative picture, but the universe, as it often does, had other plans. The story of cosmic expansion is inextricably linked with the astronomer Edwin Hubble and his groundbreaking work at the Mount Wilson Observatory in California. In the 1920s, Hubble, using the powerful Hooker telescope, the largest of its time, was meticulously observing what were then known as spiral nebulae. There was intense debate about their nature. Were they relatively nearby clouds of gas within our own Milky Way galaxy? Or were they distant, independent island universes, entire galaxies in their own right? Hubble's meticulous observations of Cepheid variable stars within these nebulae provided the crucial breakthrough. Cepheids are remarkable stars whose luminosity fluctuates with a precise, predictable period, and this period is directly related to their intrinsic brightness. By comparing their apparent brightness, how bright they look from Earth, with their known intrinsic brightness, Hubble could calculate their distances. His findings were monumental. The Andromeda Nebula, for example, was found to be hundreds of thousands of light-years away, far beyond the confines of the Milky Way. These nebulae were indeed other galaxies, vast star systems comparable to our own, scattered throughout the immensity of space. This discovery alone dramatically expanded our conception of the universe's scale. But Hubble didn't stop there. He began to analyze the light coming from these distant galaxies, using a technique called spectroscopy. When light from an object is passed through a prism, it splits into its constituent colors, a spectrum, much like a rainbow. Within this spectrum, specific elements absorb light at characteristic wavelengths, creating dark lines. Hubble noticed something peculiar and consistent about the spectra of most of these distant galaxies. Their spectral lines were shifted towards the red end of the spectrum. This phenomenon, known as redshift, is analogous to the Doppler effect for sound waves. Just as the pitch of an ambulance siren drops as it speeds away from you, the wavelength of light from an object moving away from an observer is stretched, making it appear redder. The greater the redshift, the faster the object is receding. What Hubble found was a stunning correlation. The farther away a galaxy was, the greater its redshift, and therefore the faster it was moving away from us. This wasn't just random motion, there was a clear, systematic pattern. It wasn't that galaxies were simply flying away from us specifically, as if the Milky Way were some unpopular cosmic entity. Rather, it implied that the very fabric of space itself was expanding, carrying these galaxies along with it, like raisins in a rising loaf of bread. Every raisin sees every other raisin moving away from it, and the farther away the raisin, the faster it appears to recede because there's more dough space expanding between them. This was the first direct observational evidence for an expanding universe, a concept that had been predicted theoretically by physicists like Alexander Friedmann and Georges Lemaitre, who had explored dynamic solutions to Einstein's general relativity equations. Einstein himself, initially resistant, eventually called his introduction of a cosmological constant to keep the universe static his biggest blunder. The implications were and remain staggering. If the universe is expanding, then in the distant past, it must have been smaller, denser, and hotter. This line of reasoning, when extrapolated backwards, leads directly to the concept of the Big Bang, a moment of unimaginable density and temperature from which space and time, as we know them, originated and began their outward journey. But the immediate question that arises, the one that continues to challenge our intuition, is about the into. If this cosmic fabric is stretching, what is it stretching into? Is there a void, an emptiness beyond the expanding universe? This is where our everyday analogies start to break down. When we think of a balloon expanding, it expands into the air around it. When an explosion occurs, debris flies outwards into the surrounding space. But the universe isn't an object expanding within a larger, pre-existing space. According to our current understanding based on general relativity, the universe is all of space and time. It's not expanding into anything, rather space itself is being created or stretched between galaxies. Imagine the surface of that balloon again. For a two-dimensional creature living on that surface, their entire universe is the surface. As the balloon inflates, the surface area increases, and the distance between any 2 points on the surface increases. The twoed creature wouldn't perceive the balloon expanding into a third dimension of air, they would simply observe their twoed universe getting bigger. Similarly, we as three-dimensional beings observe our three-dimensional space expanding. There may not be an outside in the way we intuitively picture it. The universe could be finite yet unbounded, like the surface of the Earth. You can travel in any direction on Earth's surface and never reach an edge. Yet its surface area is finite, or the universe could be infinite, in which case an infinite expanse is simply getting even more infinitely expansive. Both possibilities are consistent with the observations of expansion, though determining the ultimate geometry and extent of the universe is one of cosmology's greatest ongoing challenges. The expansion itself isn't into a pre-existing void, it's an intrinsic property of space-time itself. A dynamic unfolding of the cosmos that began some 13.8 billion years ago and continues with gathering speed to this very day. The fundamental mystery is not so much what it expands into, but the very nature of this process and what it implies about the ultimate structure and fate of reality. The question of what, if anything, lies beyond the observable universe, or what the universe is expanding into, forces us to confront the limits of our current scientific understanding and enter the realm of theoretical physics and cosmology, where ideas become increasingly abstract and frankly mind-boggling. If space itself is expanding, the concept of an outside becomes incredibly tricky. Our observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is vast, about 93 billion light-years in diameter. But this is just the part we can see. The actual universe could be much larger, possibly even infinite. If it's infinite, then it's always been infinite, and it's simply becoming more infinite, a concept that plays havoc with our everyday intuition. One way to conceptualize this without resorting to an outside is to think about the geometry of the universe. General relativity tells us that space-time can be curved by mass and energy. On the largest scales, the universe appears to be remarkably flat, meaning that, on average, Euclidean geometry, the kind we learn in school, where parallel lines never meet, holds true. If the universe is perfectly flat or open, negatively curved, like a saddle, it would be infinite in extent. In this scenario, the expansion is simply the stretching of this infinite fabric. There's no edge because there's no end to it. Imagine an infinitely large rubber sheet being stretched. Every point on it moves away from every other point, but there's no boundary it's expanding past. However, if the universe has a slight positive curvature, like the surface of a sphere, then it would be finite but unbounded. Just as you can circumnavigate the Earth without falling off an edge, you could, in theory, travel in a straight line in a positively curved universe and eventually return to your starting point. In this model, the universe is self-contained. Its expansion means the volume of this finite, unbounded space is increasing. Again, there's no into because the universe encompasses all of its own spatial dimensions. Current observations from the cosmic microwave background radiation, the afterglow of the Big Bang, suggest the universe is very close to flat, meaning it's either perfectly flat and infinite, or so unimaginably vast that its curvature is undetectable to us, much like how the Earth appears flat to someone standing in a field. But what if our universe is just one part of a much larger structure, a multiverse? This is where theories become more speculative but offer intriguing possibilities. One idea, stemming from theories like eternal inflation, suggests that our Big Bang might have been just one of many bubble universes forming in a larger, eternally inflating superspace, or bulk. In this scenario, our universe is expanding, and perhaps these other bubble universes are also expanding, potentially with different physical laws and constants. Our universe would be expanding within this larger bulk, but this bulk itself isn't necessarily space in the way we understand it. It could be a higher dimensional realm. If this were the case, then our universe is expanding into something this higher dimensional bulk or metaverse. However, detecting or interacting with these other universes where the bulk itself is currently far beyond our technological capabilities, and some argue it may be fundamentally impossible, making the multiverse hypothesis difficult, if not impossible, to test directly. Another fascinating though highly speculative concept is the holographic principle. This idea, arising from studies of black hole thermodynamics and string theory, suggests that the information content of a volume of space can be entirely encoded on its boundary, like a hologram. Some physicists have taken this further to suggest that our entire three-dimensional universe could be a holographic projection of information residing on a distant two-dimensional surface at the cosmic horizon. If this were true, the expansion of our universe could be a reflection of processes happening on this boundary surface. What it's expanding into might then be reversed as what is the nature of the underlying system from which our holographic reality is projected and whose dynamics manifest as cosmic expansion. This is a deeply philosophical and mathematically complex area of research, pushing the very boundaries of what we mean by space and reality. The concept of dark energy also plays a crucial role in this discussion. In the late 1990s, astronomers discovered, much to their surprise, that the expansion of the universe is not slowing down due to gravity, as had been expected, but is actually accelerating. This acceleration is attributed to a mysterious force or energy field, dubbed dark energy, which permeates all of space and has a repulsive gravitational effect. We don't know what dark energy is, but it makes up about 68% of the total energy density of the universe. Its existence implies that the stretching of space isn't just a passive coasting from the Big Bang, it's an active, ongoing process being driven by this enigmatic component. If dark energy continues to dominate, the universe will expand at an ever-increasing rate. This leads to some unsettling future scenarios. Galaxies not gravitationally bound to our own local group will eventually recede from us faster than the speed of light, not violating relativity, as its space itself expanding, not objects moving through space faster than light. Eventually they will cross our cosmic event horizon, meaning their light will never be able to reach us again. The universe, from our perspective, will become increasingly empty and dark. This accelerated expansion driven by dark energy further complicates the expanding into question. If space can be imbued with an intrinsic energy that causes it to expand, then the nothing it might be expanding into could paradoxically be the very source of its expansion. If new space constantly comes into being with its own dark energy, it's a self-perpetuating process. The vacuum of space itself isn't truly empty, it's a seething cauldron of virtual particles, and apparently, this pervasive dark energy, perhaps the expansion, is simply the universe unfolding more of its own inherent potential, creating more itself from the properties of the vacuum. The difficulty lies in our ingrained tendency to imagine a container for the universe. We struggle to think of a system that is its own container and simultaneously generates more of that container. Science is still grappling with these fundamental concepts, pushing the boundaries of physics to try and formulate a quantum theory of gravity that could unite general relativity, the theory of the large, with quantum mechanics, the theory of the small, and perhaps shed light on the origin and nature of space-time itself, and by extension its expansion. As our universe continues its relentless accelerated expansion, the ultimate fate and the philosophical implications become subjects of profound contemplation, often leading to more questions than answers. If the universe keeps expanding, driven by dark energy, what does this mean for everything within it? Several scenarios for the end of the universe, or at least the end of a universe recognizable to us, have been proposed, each more unsettling than the last, and each tied to the nature of this expansion. The currently favored scenario given the ongoing acceleration is often referred to as the Big Freeze or heat death. In this future, as galaxies recede beyond our cosmic event horizon, the observable universe will become increasingly sparse. Stars will eventually exhaust their nuclear fuel. One by one, over trillions upon trillions of years, white dwarfs will cool into black dwarfs, neutron stars will decay, and even black holes themselves are theorized to evaporate over unimaginably vast temescals through Hawking radiation. The universe will approach a state of maximum entropy, a cold, dark and featureless void, devoid of complex structures or processes. In this scenario, the universe expands into an eternity of cold emptiness. There's no grand collision or dramatic end, just a slow, inexorable fade to black. What awaits our growing universe? In this view is a future of ultimate isolation and decay, a final state of thermodynamic equilibrium where nothing interesting can ever happen again. The expansion leads to a dilution of energy and matter to such an extent that the universe effectively dies a quiet death. A more dramatic, though currently less likely, possibility is the Big Rip. This scenario depends on the nature of dark energy. If dark energy is a phantom energy whose density increases as the universe expands, its repulsive force would grow stronger over time. Eventually, this force would become so powerful that it would overcome all other forces. First, it would tear apart galaxy clusters, then individual galaxies like our Milky Way. Stars would be ripped away from their orbits, planets would be flung from their stars, and in the final moments, the force would be strong enough to overcome the electromagnetic forces holding atoms together, and finally, even atomic nuclei would be torn asunder. In a Big Rip, the very fabric of space-time itself is shredded. What the universe expands into here is, quite literally, oblivion, a complete disintegration of all matter and structure into fundamental particles. With the scale factor of the universe becoming infinite in a finite time, it's a violent end, where the expansion becomes catastrophically runaway. Then there's the Big Crunch, which was a popular idea before the discovery of accelerated expansion. If the universe contained enough mass and energy, gravity could eventually overcome the expansion, causing it to slow down, halt, and then reverse. The universe would begin to contract. Galaxies rushing towards each other, culminating in a cataclysmic implosion, a sort of Big Bang in reverse. Some theories even proposed a Big Bounce, where the Big Crunch could lead to a new Big Bang, creating an oscillating or cyclic universe endlessly expanding and contracting. While current evidence for accelerating expansion makes a simple Big Crunch unlikely, some more complex cyclic models incorporating dark energy or other exotic physics still entertain this possibility, where our universe might be one phase in an eternal series of expansions and contractions. In this case, what our universe expands into before contracting could be seen as a preparation for its own rebirth, a cosmic inhale before another exhale. These varying fates highlight how deeply intertwined the question of what it expands into is with the question of what is its ultimate destiny. If the universe is truly infinite and flat, expanding forever, then it's expanding into an infinite future of itself. If it's a bubble in a multiverse, its expansion might eventually collide with another bubble, or it might simply expand indefinitely within the larger bulk space. The philosophical implications are immense. Our existence seems to be a fleeting moment in an incomprehensibly vast and dynamic cosmos. The fact that the universe is expanding, and acceleratingly so, means that much of what exists will eventually become forever inaccessible to us, lost beyond a horizon we can never cross. This cosmic loneliness is a sobering thought. What awaits our growing universe is in many ways a deeper understanding of its own fundamental laws. The very act of asking what it expands into pushes the boundaries of physics. It forces us to question our assumptions about space, time, and reality. Perhaps the nothing it expands into is not a void in the traditional sense, but a state of potentiality from what new space, imbued with dark energy, continuously emerges. Or perhaps the question itself is ill-posed, a limitation of our language and intuition, which evolved to deal with finite objects in a seemingly static local environment, not the mind-stretching realities of cosmology. The search for answers continues. Telescopes like the James Webb Space Telescope peer further back in time and space than ever before. refining our measurements of the universe's expansion rate and searching for clues about its earliest moments and its ultimate composition. Particle accelerators smash subatomic particles together, hoping to uncover new physics that could explain dark energy or the nature of space-time itself. Theoretical physicists continue to develop new mathematical frameworks, from string theory to loop quantum gravity, that might one day provide a complete picture. For now, as we gaze up at the night sky, we are looking at a snapshot of an ongoing process. The light from distant galaxies has traveled for billions of years to reach us, telling a story of a universe that was different in the past and will be different in the future. The expansion is a fundamental character of this story. It's a reminder that nothing is static, that change is inherent to the cosmos on the grandest scales. What our growing universe ultimately expands into may remain a profound mystery, or it may be a puzzle that future generations, armed with new knowledge and new ways of thinking, will finally solve. Until then, the expanding universe serves as a constant source of wonder, a testament to the vastness of the unknown and the unceasing human drive to comprehend our place within it. The journey of discovery is far from over. In many ways, it has only just begun, stretching out before us like the expanding cosmos itself, as the cosmic tapestry continues its inexorable unfurling, carrying galaxies further and further apart. A sense of serene immensity settles in. The distant starlight, a whisper from epochs long past, paints a picture of a universe breathing, expanding into a future we can only sketch with the broadest strokes of theory and imagination. Perhaps there is no external void, but simply the universe becoming more of itself, an endless unfolding governed by laws we are only beginning to decipher. The silence of deep space isn't empty, it's pregnant with the echoes of creation and the quiet hum of ongoing expansion. Let your mind drift on these cosmic currents, feel the gentle pull of an ever-growing reality, and find a strange comfort in the vast, beautiful and ultimately mysterious nature of it all. The questions remain, but so does the wonder.